So that's great for a perfect data set like this. Obviously, this example is completely irrelevant. Why would we want to recreate a model we already know? The fundamental issue with machine learning becomes errors and noise. Because we're never going to be working with perfect data, okay? Especially for us. Not only we have errors in data gathering, right? We have noise in any natural system. So we're never going to have these perfect models. So I want to show you now what happens with training and noisy data and what the exact limitations are of the machine learning paradigm. Because the machine learning paradigm is basically this. Because computation is cheap, and because our computers are extremely powerful, we can use infinite complexity models. So in this case, the data is cubic, right? So once we get to a cubic model, we're done. We can use a 4th, 5th, 6th, 7th, 8th order polynomial, but it's never going to fit the data any better than this. But we could potentially. There's no limit to the complexity of the model, right? We can use any complexity we want forever. So in that seems very promising, but there's a huge pitfall that happens with noisy data. I'll show you what happens there. So here I've taken the same exact data. This is our red original data. I've just added a random number to it. This is noise, right? So this is our blue. This is our new data. And you see that it has the same kind of characteristics. It just has a little bit of noise or error built into it. This is what our model for any data we're ever going to use. We never can assume perfect data, right? So I'll show you what happens with our polynomial model as we train based on now the blue points. Okay, so red is our cubic. And here you can see what I'm doing in Python is I'm running the same model, but instead of specifying the degree, I'm running through these 3 iterations. I'm doing a cubic model, I'm doing a 7th degree polynomial, and a 10th degree polynomial. And here they are. Red is cubic, green is 7th, and blue is 10th order polynomial based on these blue points. So can anyone tell me which is a better model? Who thinks it's 10th order? The one that goes through every point perfectly. Is this blue line the best model of the data? Who thinks it's 7, the average? Okay. Who thinks it's 3, the red? There's no fundamental reason why any model is better than the other. But we need an answer, right? Because we're going to be using these in an applied approach. We need an answer to which is a better model. And for this, we get into heuristics. Okay? You know what heuristic is? It's just a rule of thumb. There's nothing fundamental. Right now, we've been just covering kind of fundamental theories of learning. There's nothing in the fundamental theory of learning which says which model is better for this set of data. Okay? Because we have a lot of different criteria. Which one goes through all the points? Obviously, it's the blue one. You know, maybe it's red because it's more general, or maybe it's green because it's a compromise. There's no fundamental reason. But in terms of heuristics, there is a right answer. Okay? And basically, for the heuristic approach, or for a best practice approach, the model that is best is the one which generalizes the best. So here, the black points are training data, right? And we want to know the model which will generalize beyond the training data. So when we apply it to data that's not in this set of black points, but is a part of the same system, the one that's going to more accurately predict those points. So in this case, I kind of tricked you guys a bit, because in this case, we can't really know, because we're using all of our points to train. And actually, you know, if we look at this kind of limitless complexity, even with something as simple as a polynomial model, for any given amount of data, we can always model the data perfectly, right? Because all we do is we take the number of points and we set that to the degree, okay? So if we have 20 points, we can have a 20th order polynomial that perfectly goes through every point. The issue becomes, when do we draw the line between when a model is modeling the system and the modeling is modeling the noise? And the noise we don't want to model because it doesn't generalize. It will not, the noise is particular to those data points and is not representative of the bigger system. And for machine learning as an application, the main point is generalization. We want to be able to predict, remember? That's our criteria. We want to predict things we don't know. All right, so that's the criteria, something that generalizes. In order to do this, this is just to show you the mean square error, right? It decreases. So by the mean square error, of course, the 10th order of the best model has 0 error.